Hey, let's talk about vapor pressure and changes in physical state. So, how do the properties of matter discussed thus far in our unit on liquids and solids, how do they affect state changes? We've been discussing this all along through our observations about solids and liquids, but we need to look a little further into the consequences of those forces. So, vaporization is an endothermic process. Uh, when we use the word evaporation, that implies more about the endothermic nature of a liquid gathering energy and then leaving whatever surface it's on or whatever it's in the form of a vapor with particles moving faster. Um, Energy is required to overcome these IMFs. And when it does, you think about water, particularly in the liquid phase, you have unstable hydrogen bonds. When water is able to overcome those bonds and theoretically not have any more hydrogen bonds, it's in air. It's alone in space. But to do so, we have to gain potential energy in that molecule so it can wrest itself from that bond or that hydrogen bond. We use the heat of vaporization as a value for all pure substances to describe that energy. The energy is required to vaporize 1 mole of a liquid at a pressure of 1 atmosphere. Um, Again, the word evaporation implies that cooling process where the liquid particle gains energy, flies away, and takes energy from the surface. That's evaporation. But plain old vaporization is liquid going to gas or to vapor. The heat of vaporization of water is a very large number, about 40 kilojoules per mole. You can compare that or contrast it with the delta heat of fusion of water, which is about 6, which kind of leads you to understand um, that melting water requires a whole lot less energy than vaporizing it, which makes sense if you've ever made spaghetti. So, um, with make sure a couple terms are clear here. Let's talk about condensation. Is a process by which a vapor molecule becomes a liquid. Kind of the opposite, right? So knowing that, look at this little diagram. This is just the implies the fact that the vapors that form in a closed space are always reforming molecules of the liquid, and the liquid is always evaporating, and that's the dynamic equilibrium that exists. And so let's look at a graphic that illustrates that equilibrium formation. If you harken back to kinetics, you remember that when a reaction or a process begins, you have a forward rate right away and you don't have a reverse rate. Well, same thing's true here. Initially, we have a rate of evaporation, and that stays whatever it is um, as a function of the substance that's evaporating. But your condensation starts at nothing, and then as vapors form, of course, condensation increases until it reaches that same equilibrium value, and then you have your dynamic equilibrium and your vapor pressure value. So dynamic equilibrium rate of condensation is equal to the rate of vaporization. Again, it's always happening in both directions. The vapor pressure is the pressure of the vapor present at that equilibrium value. We measure that with a barometer. And in 2018, it's a little different than it was a few hundred years ago, but a few hundred years ago, it was mankind's attempt to do things in a very visible way because we didn't have the metrics and the tools we have now. But it turns out the tools back then were pretty effective. We find vapor pressure by calculating atmospheric pressure and then taking from that the pressure inside a plain mercury column uh, with um, with a vacuum. So keep in mind that the word volatile we'll use periodically means liquids which evaporate rapidly and have a high vapor pressure. So this is that mercury barometer I was talking about. So if you look to the left here, and I'll give you a little bit of a I'm talking about this guy here. This is a vacuum in which initially what had happened was you had a glass bowl full of mercury. You take your gas collection tube, which is closed on one and opened on the other, and we will then take it out of the container. We will fill it with mercury to the very top, cap it with our thumb. Now, you wouldn't actually do this because mercury is toxic to you, but we can suspend disbelief for a minute, right? You would then place the open end of your mercury tube into your bowl of mercury, and then you would allow the mercury to fall whatever distance it does due to gravity. And this space above will be a perfect vacuum. And the height in this column would be from the surface 760 millimeters when you're perfectly, technically, theoretically at sea level. So 760 torr is the same thing as 760 millimeters of mercury. Torr stands for Torricelli, one of the people who first did this. Um, so cool, he got a unit named after him. But actually, since it's a little t, it's no longer really Torricelli. Anyway, if we instead put a little bit of water in, then fill it with our mercury, and the quantity of water you put in really doesn't matter, because water only puts out a certain vapor pressure in a given space at any temperature. So we put a little water in and then we fill it with mercury. We see that our space is a little larger. Now, um, our height, 760 of the height came from just the vacuum. So the additional 24 must have been from the water vapor. If we look at ethanol, two carbons, ethanol, we see that our height went down even further, and that additional height came from the ethanol, 65 torr. So our height dropped to 695. So a little further down, we have diethyl ether, which is a relatively nonpolar solvent, and large difference. We see that we only have a height of 215. So 760 215 gives you the 545 Torricelli from diethyl ether. So let's compare those based on properties. Water is really polar and has the smallest mass and forms hydrogen bonds. Ethanol is still polar, but it's not quite as attractive to itself as water is, because it's got a kind of a nonpolar end and a polar end. Um, and it has a medium mass and forms hydrogen bonds also. But again, evidence here just in the substance's behavior. If you want to decide which one has stronger intermolecular forces, then this gives you strong evidence that water must have stronger IMFs, because it provides less vapors or fewer vapors at the same temperature as ethanol does. Diethyl ether, on the other hand, provides a large difference and is obviously has nowhere near the attractive forces between molecules that water or ethanol have. So a very interesting experiment there. Vapor pressure is affected by two factors. Number one, molecular weight. At a given temperature, heavy molecules have lower velocities than light molecules and thus have a lower tendency to escape from the liquid surface. A liquid with a high molecular weight tends to have a very small vapor pressure. A lot of reason in that. Intermolecular forces, also a huge factor. Molecules with strong IMFs tend to have low vapor pressures because they need lots of energy to escape their IMFs. Here's some graphical comparisons of diethyl ether, ethanol, and water, and note that you have temperature changing across the x and then vapor pressure changing on the y-axis. Then we have a more advanced metric that's more meant for the calculations involved with vapor pressure, natural log of vapor pressure versus the inverse of temperature in Kelvin, and we see some differences in the linear plots. So really not a whole lot to do here, but make the observations you wish to make. Vapor pressure increases with temperature, higher kinetic energy, but it is not a direct relationship. So really just want to make this quick association. Notice we have a Boltzmann distribution with kinetic energy, number of molecules with a given energy again, and so if we increase the temperature to T2, we see we have more particles with the energy sufficient to form vapors. Couple of factoids. You don't need to be able to do any of the math solving vapor pressure and temperature. Don't worry about that. It's in the textbook. Not a concern. Important, below 0 Celsius, the vapor pressure of ice is less than the vapor pressure of liquid water. You might be saying, wait a minute, ice has a vapor pressure? Well, of course it does. It does because you still have water there, and water is a relatively light molecule. And so it's able to escape. If you ever lived anywhere where there is snowbanks in the wintertime, you know that while it stays freezing and there's snow out, that the snow goes somewhere, and it doesn't go down the hill in streams. Often you see that snow disappears on its own, and that is sublimation of water vapors from ice. And of course, you have a lot of the climates where that takes place. They get very, very dry in the winter, so it also facilitates vaporization of ice because there's very, very low moisture in the air. So knowing that, it stands to reason that the higher the temperature outside, the greater the vapor pressure the liquid would offer. Again, another term, sublimation. You guys have seen this 100 times with dry ice, but if you get bored, get on the YouTube and look at argon in solid state. Pretty fun stuff. A couple of Eastern European dudes with a cylinder of solid argon looked like they had a fun afternoon. Trust me, it's worth a minute. Okay, heating curves. I know you're all masters at this, but this needs a little bit of attention. Heating curves, and also the sister of this, the cooling curve, are a plot of temperature versus time for a process, in this case where energy is added at a constant rate. A cooling curve, energy would be removed at a constant rate. So I'm just going to briefly go through the values you need to understand. And this is just for water, but you could conceivably be asked about a different substance and be given its core values in order to calculate energy required to take it from one state to another. So to calculate the temperature change of solid ice, you would need the specific heat of ice, which is about 2.1. And you could use the heat formula Q equals mc delta T to calculate that value in terms of joules. Then you would need to calculate the heat of fusion of ice to water, which is used as 6.02 kilojoules per mole. Now you used grams in the ice conversion, so we would need to convert to moles, note the kilojoules, and make your conversion there. To heat water, you would use Q equals mcat again, using the specific heat for water. To calculate the heat of vaporization, you would do your mole value times 40.7 kilojoules per mole, huge value. Again, note kilojoules and moles. And then we would need to calculate the however higher temperature might go with steam formation using the specific heat for steam, 2.0 or 0.1, depending on who you talk to. So those are 5 different unique values you must have in order to calculate temperature or energy values required for temperature change in water. These are unique to water. Okay, if somebody starts talking to you about ethyl acetate, they're going to have to provide these values. They will not be the same. So, factoid, temperature remains constant during a phase change. You learned that in 3rd grade, 5th grade, 6th grade, 8th grade, 10th grade, and here we are again. It'll happen again in college. Heating curves. Features 3 sloped regions, 2 flat regions. Temperature is constant. The phase change. Whoops, I did it again. Sloped regions, energy input can be calculated with Q equals mcat using the specific heat of the substance in that phase in joules. The flat regions, energy inputs is changing phase. Delta T is 0 in phase change. Use heat of fusion, heat of vaporization for those 2 values. Both of them are intensive properties of matter. Both of them are calculated in kilojoules typically, although we've practiced with the joules and the mass-based versions of those units. Just make sure your units match. Always track units. This is chemistry. Enthalpy of fusion, enthalpy of change that occurs when a solid melts. Heat of fusion, it's an endothermic process. There's water's value again. The term normal melting point you'll encounter is the temperature at which the solid and liquid have the same vapor pressure at 1 atmosphere total pressure. Note that relationship. Highlighter. Same vapor pressure. The temperature at which the solid and liquid form have the same vapor pressure at 1 atmosphere. And this is called a phase change curve. You don't need to know these. These indicate the 3 phases with a diagram, and this is not profanity, sometimes referred to as a butt diagram. You can make your inferences however you want. Anyway, you see solid, liquid, gas phase indicated by the lines. You don't get these colors in typical phase change curves. But these points, normal boiling point here, where we see our pressure is equal at some temperature. And this is 1 atmosphere right here, by the way. Dot, 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 dot. And then normal boiling point, the inference we needed to make for boiling. So let's keep moving through that. Boiling occurs when the vapor pressure of the liquid equals external pressure, 1 atmosphere. Normal boiling point is the temperature at which the vapor pressure of the liquid is exactly 1 atmosphere. So there you go with normal boiling point. This is a great graphic because it shows you all the phase changes and what's called triple point here. But again, you don't really need to know this. It's just a great FYI. Let's do one calculation and then be done with this. How many joules are needed to convert 5 grams of ice at negative 15 Celsius to steam at 130 Celsius? So I'm going to go pretty quickly here, kind of noting as I go what happens. The math is in front of us. So phase changes and temperature changes. First, we're going to heat the ice to melting point. We're going to have to go from negative 15 up to 0. So our delta T would be 15. So we're going to use Q equals mcat for this line. And here it is. There's our mass, 5 grams, specific heat of ice, and 15 degrees Celsius. We get 160 joules, and I went ahead and converted to kilojoules here because that's the way I like to do it. You may do it your own way. Then we would need to melt our solid to liquid form here using heat of fusion. And so let's do that. We have 5 grams of ice. I used 18.0 for molar mass because we're not going for sig figs here, but please feel free to use 18.016. Then using our specific or heat of fusion of ice, we get about 1.7 kilojoules. Then we're going to heat liquid water to boiling point. And this time we're going from exactly 0 to exactly 100. So 100 Celsius is our temperature change. 5 grams specific heat of water, 100 degrees Celsius temperature change, 2.1 kilojoules. So for the next phase change, going from liquid to gas, we're going to need to use heat of vaporization of water, which was about 40.7, and again with our 5 grams of ice in the brief dimensional analysis. We have our molar mass conversion, then our heat of vaporization, we have about 11 kilojoules. That's a lot, isn't it? And then finally, we will need to heat the steam to the desired temperature. So we were at 100, which was boiling point, up to 130. So 30 is our delta T here. And there's our final values, 0.3 kilojoules there. And then we simply sum these up, the energy contribution for each point of the heating curve. And we get about 15 kilojoules. And that concludes this video. I hope this has helped you understand the ideas between intermolecular forces and vapor pressure. We'll see you in class.